These equivalences even go a step farther. We can start looking at our equations. And instead of using these equations we have here, we can substitute in. V becomes this. Strictly speaking, if we want to be accurate, I'd have to substitute omega r, omega not r in for V, and alpha r t, alpha r in for acceleration, but the r's all divide out, meaning that the equation I get ultimately is this one. Each of these equations substitute in. Wherever I see a v, I can substitute with an omega. Wherever I see an a, I can substitute with alpha or angular acceleration, and so on and so forth. Each of these substitutions persist, and I can even make the substitution with the centripetal acceleration we have, assuming that the tangential velocity, the speed it's going around at, is the same. Each of these substitute in, just like so. And again, we're just doing the kinematics unit, except now we're moving in circles. So, an example problem. Record players have different speeds to play record at, the most common being 45 RPM. Assuming the record is spinning at a constant 45 RPM, how many rotations would it take to play a 2-minute and 2-second long song? Okay, let's talk about this. Constant RPM right here tells me that my alpha, my acceleration, is 0. RPM is a velocity. I'll need to translate it. And this is a time. Again, I'll have to translate to seconds. And I want to know how many rotations, givens, unknowns, solve. Just there's a little bit of unit conversion here. Let's start with RPM. 45 rotations per minute. 1 minute is 60 seconds. And 1 rotation is 2 pi radians. Rotations cancel rotations, minutes cancel min, radians per second. We're good. I can put that in my calculator, solve it out. Get 3/4 times 2 pi, which is 3 pi over 2 radians per second, would be my initial velocity. T is 2 minutes, 2 seconds, which is 2 minutes. Each minute is 60 seconds, plus another 2 is 122 seconds. All I need to do is find the rotations. Well, that's really easy. I can find my rotational position, my change in my rotational position. What equation uses t, alpha, and delta theta? Or if you prefer, what equation uses alpha, omega naught, t, and delta theta? Or if you prefer, which uses change of position, delta x, v naught, t, and alpha. Regardless how you look at it, this equation right here. Delta being final minus initial. So, is how we would have done it. Now, is how we'll do it now. I'm assuming I'm starting from 0. I'm looking for how far I go. Or in other words, I'm looking for the delta. This is 0 because my acceleration is 0. So, and again, this is the radians it goes through. So if I want my rotations, I'll need to divide by 2 pi, which gives me 91.5 rotations. It's the exact same process we went through for kinematics. The only difference here is we're moving in a circle, not in a straight line or a projectile. Here's another one for you. Contestant on Wheel of Fortune gives the wheel spin, starting at the $100 space right here and going through 2 and 12/25 full rotations before coming to stop on the lose a turn space. To give the wheel initial velocity of 3.3 rads per second was the angular acceleration for the wheel. It's a kinematics problem. All it is. Where are we starting? Where are we ending? What's the acceleration? I'll give you a hint after a pause, but if you feel like you got it, go ahead and try it on your own. First thing I want to do whenever I get a kinematics problem is look for the givens, look for the numbers. I was given an initial angular velocity. I know the final, because it's stopping, is going to be 0, and I found how many trips around. Please note that I had to get into radians, and I used an exact number here, or I could use a decimal, but I like using the exact number to make my life easier. And I'm looking ultimately for alpha, my angular acceleration. From here, all I need to do is figure out what my equation is, and find my answer. Keep going, check back after the pause. Okay, if you were careful with this and went through, you should get negative 0.35 radians per second. You'll notice that I used this equation, which was previously the stopping distance equation. We're stopping, so it makes sense to use it again. I rearranged it, I plugged in my numbers, I solved. The negative is very important, it's slowing down, so do not leave that out. All in all, rotational kinematics is just kinematics again. The only difference is we're moving in circles. And we're talking about trips around a circle or trips around an orbit as opposed to moving in straight lines. Thanks for watching. Have a good one.